There's a good chance that you're familiar with the concept of a tangent line in the context of a circle. And oftentimes people think of a tangent line as a line that just barely touches the curve. And in fact, the word tangent comes from the Latin tangere, which means to touch. And the word secant comes from the Latin secere, which means to cut. And so we're going to be using both of these words in our discussions about tangent lines. And an interesting point here is to stop and ponder, why do you think we use the words tangent and secant in the context of trigonometry as those tangent and secant functions? That's an interesting question to just sort of ponder why we use those words and how they're related, how the trigonometric concepts are actually related to the concepts of tangent and secant here. Anyway, so for a circle, a tangent line is one that just barely touches the circle, and it just touches at one point. And a secant is one that cuts across. But in the context of like a curve, when we talk about a tangent curve, I think that you probably have an idea about what a tangent is at, say, some given point, like here. I think you probably have an idea of what the tangent line would be there, and it probably doesn't match this notion, the definition of what we talk about in a circle. So I want you to pause for a moment and see if you can actually imagine or actually take the moment to draw what you think the tangent line would be at that point on that curve. So if you were to try to use the definition that the tangent line only touches the curve at one point, then you might actually try to make it do this. And that is a line that touches the curve at only one point. And I think lots of people would agree that this is just not what you had in mind for a tangent curve, and it's definitely not what mathematicians have in mind for a tangent curve or a tangent line. And if you think about what the tangent line is, it's probably something kind of like this. And this line, in fact, hits the curve in more than one place. It does touch the curve, but it actually hits it in more than one place. And so, in order to answer the question of what a tangent line is, I actually want to go back down to this question down here at the bottom, which is, why do we care about tangent lines? So, as we're developing our language of talking about functions, which is really a lot of what mathematics is about, we are going to be talking about how to describe many different characteristics of functions. And if you were to describe this particular function as it is, you might say that it actually starts out rising pretty steeply, and then it hits a peak, and then it starts to decrease, and then it hits a low point, and it rises pretty quickly, and then at some point it starts rising much more slowly, and then it starts to rise more steeply again. So in describing this, I'm talking about the function increasing and decreasing, but I'm also describing how much the function increases and decreases. And we can talk about the steepness, okay? And so these are intuitive notions that we have, especially those of us who live in San Francisco. We have a good handle on steepness. But so lines are one mathematical construct where we can actually put a number to steepness, right? We can talk about lines having a slope, and here this line here has a positive slope, and this line here has a negative slope. And in talking about steepness, so we have, these are positive slope and negative slope. And these slopes are closer to 0. So this slope might be, well, I have a grid, so I could actually calculate it. This looks like, from these 2 points, it's about 1/3. This line is close to negative 1/3 slope. And this line, it's greater than 1. That's about all I can say right now. Let's see, I've got about 1, 2, 1, 1, 2, 3, 4, about 4/3. Okay, so but these numbers are bigger numbers. In absolute value. Okay, so lines, we have a calculation that we can do with lines that actually give us a numerical description of increasing and decreasing, that's positive and negative slopes, and also how steep it is, and that's the number that we use. Okay, so tangent lines are going to give us a thing that we can use to calculate or to assign a number to a description of a curve, as to be able to say it's increasing here or it's decreasing here and it's this steep. Okay, that's what this is going to give us. And so because that's what part of what we want to think about with tangent lines, we really want to think about tangent lines as being what the curve looks like at that point. And so imagine that you are a teeny tiny little microscopic insect that is sitting on this curve at that red point, and you probably don't see the whole curve. You definitely don't see over here this hill over here. All you really see is something that's right around here, and all you see is a very specific slope. And so you might think that you're on a straight line at that point. And so that's what we're actually going to take as our definition for this class, and it's a really good definition just in general to think about for all calculus, that the tangent line is the line that this curve looks like if you zoom way in. I'm going to write that. I'm going to scoot this down. Oops. The tangent line is the curve, oops, not the curve, is the line that the curve looks like I want to say ah. Okay, the tangent line at point P is the line that the curve looks like when you zoom way in to P. Okay, so we're going to say the tangent line at a point P is the line that the curve looks like when you zoom way into P. And that's a really good definition to keep in mind as an intuitive definition. Okay, so and I also want to talk about secant lines because we are going to talk about secant lines here. But looking at the tangent line at point P, the tangent line is, if you were to zoom way into that point there, you would really see that the curve looks a lot like that line there. Okay, so a secant line in general is going to be, and we're going to use secant lines, a secant line is not just a line that cuts through a curve like it does in a circle, but it's one that's generally going to go through 2 points on the curve. So a lot of times we might have 2 points here, and then, interesting. I know why. Okay, and then a secant line would be a line that goes through 2 points on the curve, like that. Okay? All right, so now here's the question, which is, how do we actually calculate how do we actually find a tangent line to a curve at a specified point? All right, so the way we're going to do this, we're going to start at this point P, and this is going to be at some point A, where the input coordinate is A, and then the output coordinate is going to be f of A. Okay, so this is the point A, comma, f of A. Okay? And the way that we're going to approach finding the tangent line at that point, we really want to think of it like, it's kind of like this-ish. That's our goal. And what we're going to do is we're going to go a little ways away from A. Maybe we're going to hit some other point B. Okay. And we can find a secant line from A f of A to B f of B. And so we're going to start with the slope of the secant line. And that is going to be the difference in y values divided by the difference in the x values. So the rise over the run. So I'm going to say f of b minus f of a all over b minus a. We're going to call this slope, and I'm just going to label it AB because it's the slope of the line that's defined by the two input values A and B. And the idea of this is that the secant line is going to get closer and closer to the tangent line if we make B closer and closer to A. Okay? The secant line will become closer to being a tangent line if we move B closer to A. All right? And the closer we move to B to A, the closer approximation we have for the slope of that tangent line. And notice we can't actually make B equal to A, because if we make B actually equal to A, it will have, this slope will be undefined, because I will have f of A minus f of A divided by A minus A, which is 0 divided by 0, which is undefined. Okay, so I'm just going to put that note. All right, and this is actually part of our motivation for some of the work that we're going to be doing in Chapter 2, which is calculating limits. And I'm going to actually write here this in the notation of limits. We can say the tangent line has a slope that is the limit of the slope of the secant line as B approaches A. Okay, and I'll write down the I'll write this down here, the slope of the tangent line. Why don't I just write it M in red? Let's call this slope M. So M is equal to the limit as B goes to A of that slope of the secant line, f of B minus f of A all over B minus A.